Alright, here's the second installment of this joyous stuff. This is 9.2. This one is angles and radians. And what this basically is, you guys have dealt with radians before in geometry class, but your calculator has two modes. It's got an angle mode, or a degree mode, and it's got a radian mode. Typically we're used to dealing in degrees. That's what most trig functions are, but we have to get used to dealing with radians, and especially if you're going to take calculus next year, radians are going to be super, super important. So just kind of make sure about that. But basically, they're just different ways to measure something. You know how there's yards and there's meters? They're technically different, but they're still a way to measure something. So, before we start with that, there's basically a big way that we have to determine angles. So, we have a general graph. On that general graph, what we're really looking at here is now we have an angle. The angle is going to be on the graph. Every one of our angles is going to start right there. That's where every one of them is going to start. That's, you know, the origin. That's just easy enough for us to do. The angle is going to look like this. Okay? This side right here is called the initial side. The initial side is where something starts. Sorry about my handwriting, I can't write on this thing. The initial side is where the angle starts. It's always going to start on the positive x-axis. Always going to the right. It will always look like this. Okay? Anyone that you see from me, it will look like that. Angles also always open counterclockwise, which means that they are always going to open like this. If it opens counterclockwise, that means the angle is going to be positive. If it opens clockwise, that means it's going to be negative. So if the angle opens any other direction, that's going to end up being negative. If it opens from the initial side to the left, that means it's going to be positive. Okay? And finally, the last term that we have to kind of know with this thing, sorry if you can hear my kids screaming down there, they're watching Frozen or something. That thing right there is called the terminal side. That's where the angle stops. Okay, so we've got the initial side, we've got the terminal side, and we know that if it opens left counterclockwise, it's positive. If it opens to the right, that means it goes negative, so it's going to be counterclockwise. Now, a couple things to think about. Angles can be more than 360. That means that they can open up. Think about the arms on a clock, how the arms in a clock go around and around and around. It's not just moving 360 degrees. It's technically moving, if it revolves twice around the entire face, it's technically moving 720 because it's gone around twice. It may look the exact same, and that's okay, but when you think about this, just think, angles can be more than 360 degrees. They can also be less than 360 degrees, which just means that they're negative. Okay? So just to look at a couple angles, here's an angle that's 240 degrees. If I look at this, my initial side is always going to start out in the same spot. So initial side is always going to go like this. But now, 90 degrees is that y-axis on top, 180 degrees. This thing right here is 270, which means that that's actually a little too much. So it's got to be a little less than 270, which means that it's probably going to look like this. And the way that we denote that, saying that it opens like this, is 240 degrees. Okay? The next thing is, let's say that we have another angle. That other angle maybe is 500 degrees. So this is really the same thing. It's going to look the exact same as 500 minus 360, and 500 minus 360 is 140. It's going to look almost the same as a 140 degree angle because it's just going around in a different way. So my initial side is always going to look like this. 140 is going to be somewhere over in here, but now the way that I write this is I go around and then I go back up. That squiggly makes it look like it's going around the entire axis one full time for 360 degrees, and then you tack on 140 more, which makes it 500. Now the very last one that we're going to do for this is a negative. So if we have like negative 30 degrees, it doesn't matter what it is. Negative 30 degrees looks like this. I've got my initial side. Oh, that's a different color. That's going to bug some of you guys. I've kind of missed being able to bug you guys. So I go like this. Negative means that it opens the other direction. Negative 30 looks like this. And I just draw the arrow to denote that it's going to look like that. And then somewhere on there I would write 30 degrees to show that it's a negative angle. Okay? Now, this kind of, like, you see how I said right here, 500 and 140 are kind of in the same spot? That introduces the idea of something called a coterminal angle. A coterminal angle, if you want to write this definition down, a coterminal angle is an angle in the, oops, so I wonder if you heard that one, an angle in the same spot. So it's an angle in the exact same spot as another angle. So that just means it's an angle that's either gone one full spin around or one spin around the other direction. So here's how we can write 30 degrees basically 3 different ways. Sorry folks, not sure where I left off. My groceries just got delivered, so if you heard my wife yelling my name, that's why where I had to go. So I'm not really sure exactly what I just said. But anyway, coterminal angles are angles that are in the same spot. So like for instance, here's 3 different ways that 30 degrees can look on a graph. So if we have 3 graphs that look like this, here's 3 different things that we could do. Okay, so number 1, notice they're all going to have the same terminal side, so they're all going to go like this. Initial side, they're all going to have the same initial side looking like this. 30 degrees normally looks like this. 30 degrees could also look like this, where we go around one time and then we come back. That's actually a 390 degree angle, but it's still the same thing. And then we could also make 30 degrees look like this, but we could go this way, which would really make it a negative 330 degree angle. So there's 3 different ways that can look. So that's just kind of what it looks like. Same spots, like this, the angle in the same spot, but a technically different angle. That is what coterminal angles actually means. Okay. The next thing to really think about is radians. So this is what radians really are, and this is where we're going to kind of get into a little bit of a trickier mindset. Okay. Now, if you remember way back to geometry, circumference is measured by 2 pi r. Now, that's where this is going to come from. This circle that I'm about to draw right now has a radius of 1. Okay? So the radius equals 1, which means that this whole thing is going to have a circumference of 2 pi, which means that the entire distance around this circle, just like this, perfect circle, is 2 pi. Alright? So the way that you think about this is, if we think about these as angles, if an entire way around this circle like this is 2 pi, then that means that the starting angle is 0, or if you go all the way around, it's 2 pi. Just like if you go all the way around a circle, it's 360. If I go halfway, it's half of 2 pi, and half of 2 pi is just pi. If I do this and split up in between, the distance between 0 and pi is pi over 2. It's just pi divided by 2. And then if I keep going on the same way, so like half pi, going here, half pi, so that's really pi plus a half pi, which is 3 pi over 2. And then finally it would go to 4 pi over 2, which is the same as 2 pi. Radians are measured in terms of pi. They will always have pi in them. They will never ever be exact. They will always be exact. They will never ever be rounded to a decimal. They will always be exact, and they will always have pi in them. Okay? Now we can convert between radians and degrees by using this very simple equation. So we have the number of degrees over the entire amount of degrees in a circle, which is 360, and the number of radians over the total radians in a circle, which is going to be 2 pi. So I have, so that's what I've got. Okay. So now the next question could really be convert 160 degrees to radians, or convert pi to radians, convert something to radians. So if I do this, I could ask to convert 160 degrees into radians. So all I'm going to do is plug that into the equation. So I get 160 over 360 is equal to, and then it's going to be the number of radians, which I don't know, x over 2 pi. And now I'm just going to cross multiply. So I'm going to go like this. So it's going to be 320 pi, and I'm going to leave that in there, equals 360x. Divide each side by 360, divide each side by 360, and now I'm going to be left with, I have to simplify 320 over 360, and that's going to simplify down to 8 over 9, and then I'm just going to leave that pi on there. So this thing will simplify down to 8 pi over 9 radians. So that's what that looks like. Okay? Let's go the other way with one, if it wants us to convert 3 pi over 5 to degrees. So this one's a little bit more challenging. There's a little bit more we have to do to it, but again, it's the number of degrees, which we don't know, over 360, is equal to the number of radians, which is 3 pi over 5, all over 2 pi. Now what this literally says on the right side is 3 pi over 5 divided by 2 pi. So it looks like this, 3 pi over 5 divided by 2 pi. Now just like we always have, I'm going to put that over 1. You guys are more comfortable seeing this in that form. So now what I'm going to do is keep, change, flip. So it's going to be 3 pi over 5 times 1 over 2 pi. And again, I'm going to cross multiply. So I'm going to simplify here and here. and then I'm going to do 3 times 1, which is 3, and 5 times 2, which is 10. So this thing right here is exactly equivalent to 3 over 10. I always take that step first, so always simplify that first. Okay, so I'm going to rewrite this as x over 360 is equal to 3 over 10. Okay, now I'm going to cross multiply, so I get 10x equals 1080. Divide by 10, divide by 10, and I get x equals 108 degrees. Okay? Now you're asking what the reason is. Why do we have to know this? What's the reason that we have to know radians? Why can't we just use degrees? You can. You can use degrees every time you want to, but it's a lot easier sometimes to use radians. And when you get to calculus, you don't have the option. You have to use radians. Okay? So the reason that this is a lot easier in radians is because we could find, if you remember back to a circle, we could find if I have something that looks like this, we can find an arc length very easily. That's that thing. Or we could find a sector area, and the sector area is all of this thing right here by 2 very simple formulas. Okay? Arc length is given by something called, oops, I should spell that right, S equals R times theta. Now R is the radius of the circle, and then theta is the degree, the angle in radians. You hear my cat? So R is the angle in radians. Okay, and then sector area is very similar. It's just A equals 1/2 R squared theta. So if we already have the angle in radians and we already have the radius, literally all you have to do is plug and chug and you're all done. You don't have to do anything really that specific. But if you don't have it in something that's super specific, you just have to convert it. So like for instance, there's a question in the book. It's a softball field that looks like this. It wants to know how much fencing they have to buy in order to help the softball field. Okay, they know that it's 200 feet all the way out to the fence. They know that it's a 90-degree angle from first base to third base. So we want to basically figure out how much of this we have to buy. So if you want that, you just have to use the sector length, or the arc length formula. So it's just going to be S equals R times theta. And now the only thing I don't know is what theta is. I know that R is 200, but if I want to know what theta is, I'm just going to convert this. So it's going to be 90 over 360 is equal to the radians over 2 pi. And now I'm just going to cross multiply. So I'm going to get 180 pi equals 360x. And then when I simplify all of this, I'm going to end up getting pi over 2 equals x. And now I'm just going to plug it into the formula. So it's going to be S equals 200 times pi over 2, and then it's going to be S equals 200 pi over 2, which that will simplify to give me S equals 100 pi. Now in this case, if it wants to know exactly how much we have to get, then that's saying it's about, it's about 314 feet. So if we have to buy that, it's about 314. Okay? Now, if you need that, pause right here, because I'm going to go back and I'm going to change this, or I'm not going to change it, I'm going to do the other one. So we go through here, and you're going to notice that, I don't think the circle tap thing works here, no. So you're going to notice that I'm going to really use pretty much the same amount of stuff to figure out what the sector area is. So this is where the work goes away. This is where it makes it really nice for us. So if I want to find the area is equal to half of the radius squared times whatever the radians was, which was pi over 2. So I'm going to go through this, and I get 200 squared. 200 squared is 40,000, and then 1/2 times that is going to end up being 20,000, so it's going to be 20,000 times pi over 2. So then when we end up multiplying that across, the 2 and the 2 are going to cancel, so it's going to be 10,000 pi. And if I get 10,000 pi, then 10,000 pi will end up just being something along the lines of 31,416 feet squared. So if we were trying to figure out how to fill that thing in, that's what it would end up looking like. Okay? So that's pretty much it for section 9.2. That one's a little bit longer than section 1 because it's a little bit different. There's a little bit more going on with it. So just kind of keep your eyes peeled on what does and doesn't make sense. If something doesn't make sense, ask me about it. Alright? So if you don't get something, ask me about it, because that's something that we can kind of work our way through together. Alright? Again, if you have any questions, I'm also going to be posting the PDFs of my notes up. I don't know if that's going to help you or not, but I'll have them up there. So if you have any questions, make sure you let me know. Otherwise, good luck, and let me know if you have any issues.